Hi guys, welcome back to another video. Today we will be covering an interesting topic of reservoir sampling, and then we will be solving two lead code problems using the code structure of reservoir sampling. And these two problems are linked list random node and random pick index. And this is the Wikipedia description of reservoir sampling, and it says that it is a family of randomized algorithms for choosing random sample of k items from an unknown size n, and it is done without replacement. And without replacement means that we cannot pick an item more than once, and this n tends to infinity, and we also cannot store these n items in the main memory because n tends to infinity. You can assume that it's a stream of data, and the population is revealed over time, and the algorithm also cannot look back at previous items. The main motivation behind this algorithm is that the given n, it tends to infinity, and if n does not tend to infinity and is already known, then we can simply select 10 distinct items between 1 and n with equal probability and just keep those 10 items. Reservoir sampling is useful for the cases when we don't know n in advance, and n can be huge. So let's try to understand reservoir sampling using a famous algorithm R. In reservoir sampling, we are going to be dealing with an infinite stream of data. In real world, you can think of it as log events, user clicks, or stock prices. So we have this incoming data, and let me represent it as S1, S2, and all the way till Sn. We are using this n so that it becomes easier to explain reservoir sampling, because n tends to infinity and it won't be possible to draw infinite items. So we have to sample k items from these n items such that each item is equally likely to appear in the final sample. So in our final sample, we have some k items, and let me call these as R1 all the way till Rk. And we only have the memory to store these sampled k items, and we don't have memory to store these items. So the probability that the first item is going to be picked in our final sample of k size is going to be same as the probability of second item being picked, and it is going to be same as the probability of nth item being picked, and this probability is going to be equal to k divided by n, where n is unknown and it can also tend to infinity. And I am going to prove that these probabilities are equal mathematically, and once we prove that, we can solve our lead code problems. So this is the main challenge for infinite stream of data, and when we want to sample k items, that we cannot store it anywhere, and when we process a particular element, we immediately discard it. So when the first item comes, we process it and we discard it, and when the second item comes, we cannot process the first item now, and when, let's say, 10th item comes, we cannot go back and access the first 9 elements. So this is what makes this problem slightly harder, and these are some bullet points why this problem is difficult. So we cannot store all the items, we don't know the size, and we see each item only once, we cannot rewind or retraverse past data, and we want a uniform random sample, and that means that the probability of a particular item being picked in our final reservoir of size k is the same as all the other items. Let's have a look at algorithm R. So this is the pseudocode of algorithm R, and you can find this on Wikipedia. So here we are given our items to sample, and this is from S1 all the way till Sn, and we have to form a final result R from R1 to Rk. So initially we just simply assign first k items in this for loop, because we need the final result to have k items. So we simply set these k items, and in the next for loop we replace these items. And the thing which ensures that the random sample is uniform is this random integer call. So what happens is, after we have set our first k items, now we iterate from k plus 1 all the way till n, and we call this random integer function, which generates an integer from 1 to I, both inclusive. So the probability that a particular integer will get selected from 1 to I interval is the same, and it's equal to 1 divided by I. And then we check in our if check, if the selected j is less than equal to k, then we simply replace that index and set si. So if a particular item from our sample has to be present in our final reservoir, then what it means that it has to escape this replacement, and we can find the probability that a particular item s1 escapes the replacement in all the I iterations. And initially, let's start by writing some of our probabilities. For random integer call, what is going to be the probability that j is going to be less than equal to k? So here our number of favorable outcomes is equal to k, and total number of outcomes is I. So this is going to be equal to k divided by I, and we have to find the final probability that j will be equal to 1 at the end. So what this means is that s1 is going to get replaced in our ith iteration, and what this means is that s1 is not going to be present in our final reservoir sample. Using Bayes' theorem, we can write this equation here. So we know that this probability is going to be equal to k divided by I. And now let's think about this probability that after this is true, that j is less than equal to k. Now what is the probability that j will be equal to 1? So it is going to be equal to 1 divided by k, because once we are in this interval, then we have k number of total outcomes and we have to just select one of them. So it's going to be equal to 1 divided by k, and we multiply both of them, and finally we get 1 divided by I. So this is the probability that s1 is going to be replaced and will not be present in our final reservoir sample. Now what is the probability that s1 will not be replaced and will be present in our final reservoir sample? It is going to be simply 1 minus 1 divided by I, which is going to be equal to I minus 1 divided by I, and this is for ith iteration. So at the end of our all the iterations, now what is going to be the probability that s1 is going to be present in our final reservoir sample? So it is going to be the multiplication of all the iterations. So this is going to look something like this, that we are multiplying from I equal to k plus 1 all the way till n, and this is the probability for a particular iteration that the item si is not going to be replaced in our final reservoir for a particular iteration. So if we calculate this, what it is going to be, it's going to be k divided by k plus 1 times k plus 1 divided by k plus 2, and if we go all the way, we are going to have n minus 1 divided by n, and with multiplication these terms are going to get cancelled, and at the end we are going to get k divided by n. So as you can see that the probability that a particular item will be present in our reservoir is equal to k divided by n. Also we can get this probability I minus 1 divided by I really easily. So if we draw our interval 1 all the way till k, and we have I here and n at the end. So what is the probability that a particular item, let's say s1, is not going to be replaced? So it's going to be simply I minus 1 divided by I. So we don't pick this, so the remaining number of items is I minus 1, and that is going to be the number of favorable outcomes, and we can divide it by total number of outcomes, which is I. I hope this mathematical explanation made sense, and if you have any doubts, let me know. I think now we are good to proceed with our lead code problems. So let's have a look at both of them. So here we are given a singly linked list, and we have to return a random nodes value from the linked list, and each node must have the same probability of being chosen. So without reservoir sampling, we can solve this problem by finding the length of the linked list. And after finding the length of the linked list, what we can do is we can use ran.nextInt and pass in the length of the linked list and generate an integer. and that integer is going to be something between 0 to length minus 1, both inclusive, and whatever the value comes in that interval, we can traverse that number of steps and return that node. And that is a pretty good solution, as it uses O of n time and constant space. The sole purpose of introducing reservoir sampling for this problem is to teach reservoir sampling. As for this problem, the length of the linked list is already known and is finite, and for reservoir sampling we deal with an infinite stream of data. So for example, I have this code for reservoir sampling, and it would look something like this, where we have an infinite loop and we are reading from the stream, and then as we are getting the integers, we are processing that and incrementing the count, and then we can use the probabilities and set our sample to that value. For this problem, we only need to sample one value, so we can use one of these three if checks, and all of these three if checks would do the job for us. So for example, for this if check, here we are generating integers from 0 to count minus 1, both inclusive, and the probability of getting a 0 is 1 divided by count. And here we have math.random, and it deals with real numbers, and here as well, probability of a particular value getting selected would be 1 divided by count. And for this one, this is the example from algorithm R. Here we take the output of math.random and multiply it by count, and then we increment it by 1, because for math.random the last value is not inclusive. For example, if the initial count is just 1, then math.random into 1 and converting it to integer is going to give us 0, and adding 1 to it would set the value of j as 1. And when the count becomes 2, then this value is either going to return 0 or 1, and we simply add 1 at the end so that it's either 1 or 2, the final value of j, and we set the sample accordingly. Now let's try to use these three code blocks and try to write the code for our getRandom function for this linked list. And as discussed, this code is not going to be a real reservoir sampling algorithm because the length of the linked list is known. So let's try to write this code. So initially I can define the head of the linked list and set this head as this dot head equal to head, and inside my getRandom I can create a length variable and a reservoir value. Let's set it as 0. At the end I have to return this reservoir, and we have to iterate over the linked list. So list node current will be equal to this dot head. For iterating, we're going to need a while loop. So while current is not equal to null, at the end I have to do current equal to current.next and increment the length. And before these two things, I can check the probabilities. So let's take this example first. So let's just copy and paste, and I have to also create this one. So what I can do, I can create this one here and then assign it in the constructor, this dot rand, and then this is going to be this dot rand, and instead of count it is going to be length, instead of sample it is going to be reservoir, it's going to be current dot val. So let's try to run this and see if everything is okay. And yeah, everything is okay. Let's try to submit it. Yeah, that works as well, just great. So this if block, it is guaranteed to run for the first node. So when current is head, so this value is going to give us 0 because initially the length is 1, and it is going to give us integers between 0 and 1, where 1 is not inclusive and 0 is inclusive. So that is why it's going to be equal to 0, and initially reservoir value would be equal to head.val. And when length becomes 2, then it is going to give us integers 0 or 1. And then what is the probability of getting 0? So the probability of getting 0 is simply 1 divided by length, and this ensures that the probability of every node being chosen is the same, and that's the case for this particular current node. Now when the length becomes 2, so this nextInt function is either going to give us 0 or 1 integer. Now what is the probability of selecting this current node? It is equal to 1 over length, and the probability for every node is going to be the same, and this is also the probability of getting this value 0 here, and it is guaranteed that if this value is being selected, we are going to get a value of 0, because initially we start with length 1 and we can only get integer 0, and after that we get either 0 or 1, and then we get either 0, 1 or 2. So this 0 here is fixed, so that is why we use this value 0 here and not other value, because this guarantees equal probabilities, and we can use this for selecting this current node's value. Now let's try to use the other if block and see what happens. So here we have if math.random, and here what I can do is I have to do math.random should be less than 1 divided by length, and then we set reservoir equal to current.val. So let's try to run this, and this works as well. Let's try to submit, and yeah, that works as well, which is great. Math.random is going to give us a real number between 0 and 1, where 1 is not inclusive. So when the length is currently 1, we are guaranteed to get a value in this interval. So initially the reservoir gets set as the value of the head node, and next when length becomes 2, then probabilities get distributed and it becomes half, and the probability of selecting the next node would become half, and if it falls in that interval, then we can pick that node, and similarly for future nodes. And let's try to use the final if block. So this if block is from the algorithm R. So here what we are doing is we are simply converting math.random result into integer, and depending on that we are setting our reservoir, and since we are only sampling one item, we can simply check if j is equal to 1, and here what's gonna happen is math.random is multiplied by length. So initially if the length is 1, then this is going to give us 0, and then 0 plus 1 would be 1, and then reservoir value would be set as head node, and when length becomes 2, this one is either going to give us 0 or 1, then j would be either 1 or 2, then it is going to distribute the probabilities equally, and then we can set our reservoir value. So let's try to run this one. So this works, and submit, and yeah, that works as well, which is great. So I hope this made sense and you got a better understanding. So again, one thing to keep in mind, that this code is not reservoir sampling, because for reservoir sampling we cannot access past nodes, and this get random call can only process the current node. But for this code we are iterating over our linked list from the beginning, and this violates the reservoir sampling principle. The main purpose for writing this code is only to teach this code block. So don't get confused between a real reservoir sampling algorithm and this code. So be careful with that and study that properly. Now let's also solve our second question of random pick index. For random pick index, the difference is that we have to choose a particular target number. So for the previous problem, we did not care about the value of a particular node, but for this problem we have to pick a target, and here the input is given in the form of array instead of a linked list. So following the same pattern from our previous problem, we can define an array and random variable and then assign them in the constructor. Initially we can set the length of the array and assign count as 0. So here we are assigning count initially as 0 instead of 1, because we have to check if the value is equal to target, and then we increment the count. For our previous problem, we didn't have to do this target check, and we were able to start with the count value of 1, and then we incremented count after our if block. And in this case we are incrementing the count before our if block. Only when this if block runs, and we can assume that the given target number is existing in the array. So there's going to be at least one index at which we can find the target value. So when we are inside of this if check, we increment the count to 1 and then we generate an integer. So when the count is 1, the integer would be 0, and then we can set that index. And if we again find the same target, then we can increment the count value, and now it is going to be 2, and the generated integers would be either 0 or 1. So the probability of getting a 0 now would be equal to 1 divided by count, and then we can set that index, and at the end we can return the index, and this is going to ensure that the probabilities would be equal for the target indexes. And this approach is going to use O of n time and constant space. And again, one thing to keep in mind, that this is not a real reservoir sampling algorithm, as the length of the array is already known, and reservoir sampling is used for an infinite stream of data. So I hope both the problems made sense and the reservoir sampling also made sense. And if you have any doubt, let me know in the comment section. And thank you so much for watching my video, and I'll see you in the next one.